Welcome all to this 12th lecture of Principles of Statistics. Today we're going to continue with the Bayesian method, or the Bayesian methodology, and so we're going to speak essentially of inference or inferential procedures that are constructed from the posterior, and then we'll also start about talking about the justification from a frequentist point of view. So, statistical inference with the posterior. And this refers to, the usual procedures that we've been talking about so far, plus prediction, which we haven't really spoken about very much, but is also, one of the main objectives of statistical inference. So with the posterior distribution, or just the posterior. Okay, so let's note, or let's maybe recall from our discussions last time that this guy, so the posterior distribution, is a probability measure, of course. So it is a probability measure with the peculiarity that it is random. So this is random through the data. Okay. So if we fix the data, then we get a probability measure, but otherwise we get a random probability measure. Okay, so due to it being probability measure, and this is of course, probability measure, so I should have said on the parameter space capital theta. So because of that, it can be directly used for inference, right? Or to construct, maybe to address, just to change the wording a bit, to address the, so the inferential procedures or problems okay. In this case about theta, right? Although it is quite important to always keep in mind what we've been sort of discussing so far, which is, keep in mind that they are, very, result. Okay, so let me just, I can't at the moment read and write clearly. So the resulting inherent subjectivity, right, through the prior. Okay, and importantly, so the lack of frequentist interpretation. And this is, of course, at least without further justification. So I'm not saying it's not, they don't have the frequentist interpretations, but at least as they come constructed from the posterior, there is no reason to believe that they will get these interpretations. So at least without further justification. Okay, so what are these inferential procedures? Well, they are the usual ones, right? So estimation, so let's then sort of mention in each case how the Bayesian methodology sort of allows us to derive inferential procedures. So in estimations, remember we just want a so-called point estimator to pin down the parameter giving rise to data. And so we're sort of taking this a bit more frequentist point of view, but without trying to justify anything, at least yet. So in estimation, okay, so we can take as a point estimator, for instance, the posterior mean. Okay, which is usually denoted, sorry, this does not right, so it would be theta n hat, which can also be as a function of the data, and this is the expectation under the posterior of theta. Yeah, so theta following that distribution, right? And we can also take other sort of other sort of points from the distribution. So when properly defined, we can also take the posterior mode, or or the median, or any of this. So when properly so the median is a bit more standard. Yeah. Okay, so what about uncertainty quantification? Uncertainty remember, this is in the frequentist language, this is confidence regions or confidence sets. So for any Cn subset of capital theta such that it satisfies that its mass under the posterior distribution is precisely 1 minus alpha, is what is called a level 1 minus alpha. And then generally you would have here confidence sets, right? But instead we get what is called a credible set. Okay. So what is this credible set? Well, so this is essentially the Bayesian version of frequentist confidence sets. Okay, and if we had a confidence set, then it has a meaning in terms of the probabilities, well, the coverage, more precisely. And so what do we mean by that? Well, I'll remind you that this is the probability under the theta naught being the true parameter that the theta naught belongs to the Cn. Yeah? And this coverage in a frequentist sense is not really clear what its value is, or whether it will be, this 1 minus alpha or something approximately close to it. Okay, so a priori, the value of this is unclear, or whether there is any pattern behind it. Okay, so 3, we get just hypothesis testing, the usual third inferential procedure we're interested in, or testing, sorry. Okay, so let me just, for consistency, this here. Okay, so now let's consider that we have, several hypotheses. So we can start, well, we can just consider 2. So consider 2 competing hypotheses. And this can be, so H0 being capital theta naught and H1 being capital theta 1, okay? Where of course the capital theta J is going to be a subset of the capital theta for, J 0 and 1, okay? So that's just the usual thing. So let's now talk about how we would choose between these hypotheses. And this is something we've seen already in the example that I gave you in the first lecture on the Bayesian methodology. And so, just to remind you, we choose H0 or capital theta naught if we have that, the following ratio is larger than or equal to 1, which is, I remind you, just the usual ratio. Okay. So if this is greater than or equal to 1. Yeah. And this has a name, by the way. So the left-hand side has a name. The left-hand side is called the Bayes factor. Yeah. And when you have more hypotheses under consideration, you have Bayes factors, plural. So, okay, so now let's just say one more thing about it. So since we get that, we have that, the probability of a capital X given a, in this case, a capital theta J equals the integral over this capital theta J of the probability of X given theta and then the prior. Okay, so given this, then we have that the Bayes factor above maybe this factor would be a bit better. So this factor is going to be equal to simply, so let's look at the expressions. Well, so then we get two integrals, right? There's theta naught, and then the probability. So maybe let's write it out directly. So this would be the product I equal 1 to n of this f. So we're writing now things in terms of PDFs. We could write them in terms of PMFs. So remember, this is just cosmetic changes. And so the same quantity, of course, for now for the capital theta 1. Yep. Okay, so now that we have this, we realize that if we divide both the numerator and the denominator by the same quantities, but as in by the integrals, but defined on the whole parameter space rather than just restricted to these guys, then what we get is simply the posterior distributions, right? Or the ratio of the posterior distributions. Okay. And this is again something we sort of saw already in the first lecture on Bayesian methodology, right? So what do we conclude from this? Well, again, this is something we saw. So this shows that, or from the left-hand side. So from the left-hand side, we see that the Bayes factor, so the factor is going to be basically a weighted form of the log ratio statistic, right? So okay, so it corresponds to a weighted form of the likelihood ratio statistic. Okay, great. So one more inferential procedure, and as I anticipated, this is Bayesian prediction. Bayesian prediction. So let's now consider, if we want to do prediction, then we want to have some random variable that depends on others, so that when we get value of these other random variables, then we can try to predict things about the first one. Yeah? Okay, so let's consider modeling as I was saying, the response, so a response variable y, or capital Y, in terms of covariate capital X, yeah. And we do so through the following relationship. So we say that y x, at least when taken together, if they are conditioned on this theta, which is random, and according to the prior, then this just follows. This has the following PDF or PMF. This is just the usual F, and this is again where theta is distributed as the prior distribution. Yeah. Okay. So then, what do we have as a prediction distribution? So then, prediction distribution is given by the following expression, which is, so we wish to find the probability of the response given the covariates. So how do we get this? Well, we need to integrate out basically all of the values of the theta, and this, of course, has to be done with the theta being, random, and taking into account the values of the covariates. Yeah. So so this is the conditional distribution. And this is, of course, the posterior distribution. Okay, so and then one more thing that we can say about this. So we can use, well, let's say, which can be used for all the above mentioned inferential procedures. So remember that, in the same way that the law of a random variable will determine, everything about it, so we'll do a PMF or a PDF when one exists. Yeah. So this is why we can then construct anything that requires distribution through the PDF or PMF, right? Okay, so enough for the different inferential procedures and how we would approach them in the first place. And let's now talk a bit more about this frequentist interpretation of things, because after all, in this course, as I said at the very beginning, this is a course in which we're going to be interested in this sort of more frequentist philosophy. Yeah. Okay, so third version is, the frequentist, third section, of course, frequentist behavior of the posterior distribution, right? Okay, so this will take us a couple of lectures, and so let me now talk a bit, maybe give an example and this kind of, give an example. And what we will do in the next lecture is to introduce and prove the Bernstein von Mises theorem, which is really the key result to justify the frequentist behavior of Bayesian methodologies. Yeah? Okay, so just to write it, so the previous inferential procedures so they can be analyzed under the the frequentist sampling assumption of the usual thing. So we have the xi's are going to be IID according to some f theta naught, some theta naught fixed, of course in the parameter space kappa theta. Yeah. Okay, so let me then give you this example. So let's go back to an example that we saw in the last lecture, which is, one in which we have conjugacy, and so therefore we can do the calculations more explicitly. So let's consider x1 to capital Xn to be IID with the Gaussian distribution or with a normal distribution. Yeah. Normal with mean theta and variance known and equal to 1. And, as Bayesians, then we elicit a prior, so we're going to say that the theta follows a normal distribution with 0 norm, so standard norm. Yeah. Okay, so we saw in the last lecture that the distribution of this is actually very well understood, and it's simply given by a normal distribution that is centered around this. So the mean, maybe the sum divided by m plus 1 rather than n if you were, if we were comparing this to the mean, and then the variance is going to be shrinking, and so this normal distribution will have will be concentrated. It will be concentrated around this sort of near sample mean. Yeah. Okay, so therefore, this guy, okay, so the posterior mean we've introduced already. So this guy, as I was just saying, is very close to the sample mean, and which is, by the way, of course, the MLE, so it is, close or almost the MLE. I remind you that the MLE in this case is just sample mean. Okay, and what does this mean? Well, this means that probably it's not too hard to analyze the behavior of the sample mean. And so let me make a claim that I will show in a second. So claim, that this guy minus, sorry, not that. So this guy minus this guy. Excuse me. So this will converge, and the theta naught and the infinite product probability measure. So this will converge to this theta naught. Okay. So indeed, and so this is what happened, of course, to the MLE, right? So indeed, under this p theta naught and the infinite product probability measure, then we get even more than that. So let's just directly prove what is more than that. And so what we can do, we can look at this quantity. So it's no surprise that we're looking at that because we sort of expect some sort of central limit theorem. And okay, so we can rewrite it. So we can add and subtract the MLE. Right, because that is the guy that we understand. And so, because we understand this guy, in particular, we know that this quantity will converge. So by the asymptotic normality of MLE, will converge in distribution to a normal distribution with zero mean and inverse Fisher information matrix at the theta naught. Okay, so that's regarding the second term. Then what about the first term? Well, the first term is actually pretty simple, right, to analyze. So this is going to be, so this we can rewrite as n plus 1 minus 1 over n of this, okay, so of the sum. Okay, and this, of course, is going to be no more than square root of n plus 1, and we get the sample mean, which is a quantity we understand well. And we can add and subtract this theta naught. Yeah? Okay, and so I mean, yeah, so then this is clearly going to 0. Yeah. the strong law of large numbers. Yeah? And this is going to go to 0 actually almost surely. Yeah? So by strong law of large numbers. Okay. So what do we get as a conclusion? So in particular, what we conclude is that by Slutsky's lemma, we get that the square root of n of this guy minus theta naught will converge in distribution to a normal distribution with 0 mean and this inverse of the Fisher information matrix. So that's great, actually. Yeah? So, and in particular, we can use this theta n hat instead of the MLE, right? Okay, and this is of course, for estimation, so this is a valid estimator in itself. Okay, so let me just make that a bit nice. So valid estimator, and not only that, so it's not only for estimation, but what we can do is for a confidence region is rather than centering the confidence region around the MLE, we can center it around the posterior mean, right? And so now we're constructing things a bit more in terms of the posterior, even though in this case it's just very, very similar, at least the estimator. So let's mention this. So we can use this valid estimator, and this is again for every sort of inferential procedure, but we do have to remember that the Bayesian is not going to use the asymptotic, the asymptotic distribution, which in this case would be something like this, but the posterior directly, yeah, and that's actually very important. Yeah? Okay. As in this case, they will both be Gaussians. And very, very similar ones, but that's only because we're in a Gaussian experiment. And if we weren't, then we would use this sort of even non-accessible distribution, yeah, for finite samples, as Bayesians at least. Yeah. So this is of course for inference. Okay. So just one more comment about this. So hence, to check precisely okay, so to check that these credible sets C and R confidence sets okay, so maybe let me write out just for clarity, even though we've seen it at the first half of the lecture. So of course the credible sets have to satisfy, so they have to satisfy this, right? Okay, and if we want to say check that they are, these frequentist confidence sets, And again, I remind you that this means that the probability and the theta naught of the infinite correct probability measure of theta naught being in the Cn, then this has to be equal to, or at least converge to 1 minus alpha as n goes to infinity. Yeah. Okay, so for this to happen, what we need to analyze, the really the entire posterior distribution. So remember that before, so in the asymptotic normality of MLE, what we were looking at is simply the distribution of an estimator. Yeah. But now we have much more than that, because we have to analyze, rather than a point that is random, a distribution that is random. Yeah? So there is, of course, an additional complexity in that. Yeah? So the posterior. Yeah. Okay. So then we end just by mentioning the Bernstein-von Mises theorem, which is what we will concentrate on in the next lecture. So the Bernstein-von Mises, so there's two people here. And von Mises is separate from von Mises. Theorem. So this is for me a I guess it's a very I would say a very important theorem in statistics, and probably very, very high up in terms of at least in the understanding of Bayesian methodologies from a frequentist point of view. So this theorem, which was, by the way, first studied by Laplace already in the beginning of the 19th century. So first studied by Laplace. Okay. And well, he was looking at precisely, cases where you have this conjugacy, so you could analyze things, but he was the first to realize, this connection. Well, not even a connection, but I was going to talk about frequentist statistics, but that didn't really exist, at least not as established as it did in the 20th century after Fisher. So I mean, there was, Laplace did have at least this is what is understood more or less now, is that he did have a frequentist understanding of things, even though this may not have been explicitly written or spoken about, because there was no such distinction. But he did understand that you could still look at what happens when the data is generated by a single parameter, and then look at these conjugate families. Yeah? Maybe not only conjugate, but more general ones. And there is, this is already in at least one of his books from the beginning of the 19th century. Yeah? Okay, so that just, I guess, as a historical remark, and just to, if it was first studied by Laplace, then who proved this Bernstein-von Mises in the, in the generality that we understand it now? Well, it was again LeCam. Yeah. So I've spoken about LeCam briefly in the previous lecture. So he's a modern god of statistics. Yeah. So LeCam improved by LeCam in its final version, if you like. Benson-Mises theorem. So what does it say? Just to give you, heads up, it says that the posterior will be approximately like a normal distribution that is centered around the MLE with the inverse Fisher information, of course, rescaled by Vn. Yeah, okay. And this is, under, so in some way, and I will comment on all of this in a second, so under this P theta naught with the infinite product probability measure. And, okay, so let me just state it all. So whenever the prior charges a neighborhood of the true parameter, and that's key. And then, of course, remember that we don't know the true parameters. So generally, what you will want is full support, at least in parametric models. Certainly, we won't talk about Benson-Mises non-parametrics because that completely changes in infinite dimensions. But in finite dimensions, we need this positive probability. Yeah? Okay, so what does that mean? Well, it just means that it is sufficient that the prior, doesn't really forget about the theta naught, yeah, for the posterior to actually then get this sort of asymptotic behavior. So what is this asymptotic behavior? Well, we have this normal distribution on the right-hand side, and that is, of course, going to be, an approximation to the posterior, but the normal distribution is random in this case, right? Because it is centered at a random point, and so, of course, it's random through the data, and that makes sense because the posterior is going to be random, right, depending on the data. So what this is saying is, well, if you, fix the data, then you will retrieve a normal distribution. If you don't fix the data, then actually, you still do, but this will be sort of shifting. Yeah. Of course, because we're now talking about, approximation of measures rather than points, as we, unlike for the MLE. So for the MLE, we were just looking at the distribution of this point. Now it's a bit more, well, it's more complicated. Then we will need to clarify in what sense do we mean this approximation. Yeah. And second, the second remark I do want to make here is that, this condition of, having sufficient mass, well, not sufficient, but just some mass around theta naught, or on theta naught, by the way, just, I guess, a little deter, is that if you look at the expression for the posterior and have that the prior is 0 around, or at a point, even just at a single point, then you get that the posterior is going to be 0 exactly at that point, right? So we, so it makes sense that at the very least we need that positivity at theta naught, and maybe it's on a neighborhood of it, yeah. And it's actually near surprising that that is enough, yeah. Because you would think, well, maybe you need a bit, you need some lower bound on how much mass you need, which is actually the case in non-parametrics, by the way. But anyway, let's not talk about that. So yeah, just as long as you have any mass, then that gives you this limit theorem, which, by the way, I mean, where is the prior? On the right-hand side. It is nowhere, yeah? So it's a bit magical that the prior really doesn't have any influence beyond what the support of the posterior will be, right? So of course, it has that influence, but that is it. So what this says is that the Bayesian methodology, even though it's it's giving us this distribution, and it's very nice because it gives us all kind of inferential procedures, but then we were worried about the subjectivity, then actually the subjectivity completely washes away up to this support of the prior. Yeah. Okay, so I hope you enjoyed the lecture, and see you again in the next one.